Well, I guess we're just going to get started. Some other people will probably pop in as we get going, but I started the recording so we can at least get that up as well. All right, so kind of as a little review where we left off, last time we were talking about the evolution of C, and we looked at that through the lens of variables. So C supports variables, arrays, and structs. So struct is kind of like a modern dictionary in some of our languages, but not quite, because we talked about side effect, which we'll bump into here in a second. But they're kind of like dictionaries. They're name value pairs. But the punchline is that the C programming language, while still used today, started having some weaknesses, and it wasn't so much that the language was bad. It had more to do with the fact that our computers kept getting more and more powerful, and human beings were using them to solve more and more complex problems, and we started getting to the point where C started creating allowed us to create solutions that were a little bit cumbersome. All right, and this is kind of where we needed that next jump, and that was where object-oriented programming came in. So we looked at kind of an example last time of what a struct was in C compared to what a class is in C++. And at the end of the day, a struct and a class, a class is effectively a struct that also has functions within it. The difference there is that, as we talked about last time, there's this idea of side effect when something is passed by value versus passed by address. So when something's passed by value, a copy is passed and there's no side effect. If something is passed by address, there is side effect. So historically, structs were always passed by value, not by address. So to say that a class, which is almost always passed by a class is almost always passed by address, to say that these things are separate is not really fair. Punchline is these guys cannot, a class cannot replace a struct exactly, as to the chagrin of the Java people, which we'll bump into here in a little bit. So in any case, so C++ comes in. Basically what they did is they added this new animal called a class. All right, and that's where we started talking about the difference between a procedural language and an object-oriented language. So C is a procedural language. C++ is an object-oriented language, and we talked about the differences there in terms of like a telephone. All right, and this kind of circles back on what I said a moment ago about that it wasn't that C couldn't let us solve the problems we needed to solve. It was that as the problems we solved became more complex, our solutions became cumbersome. All right, so imagine something like a telephone that's fairly complex, and then you can pretty quickly imagine things that are far more complex than telephones. If you had to implement a telephone as a giant pile of wires, then all of a sudden, after you get past 2 or 3 wires for something, it starts becoming kind of inconvenient to conceive of or carry around or stuff like that. You don't want them to fall apart and all this stuff. So when we talk about the object-oriented telephone, it looks like a telephone. We take all those wires and we carefully shove them into a telephone-shaped box, and we call that an object. And we only expose the pieces of wire that we actually need to directly interface with when we use a telephone. All right, so object-oriented programming languages are just there's an abstraction layer, an organizational layer sitting on top of the languages that have been there up to that point in time. It's like buying a piece of Tupperware from Walmart. Okay, human beings like to organize things as problems become more complex. So now we have languages that allow us to further organize things. Okay, so that was the evolution of C++. We kept the variables, we kept the arrays, we kept the structs. We added this new animal called a class, which on the surface appears to be a struct that could also house functions, that we can throw those functions into the inside of the struct. But the one difference there is that structs are always passed, by default, structs are passed by value. By default, objects are passed by address. So they are not equivalents, which actually becomes kind of the problem and almost the catalyst for this course, this workshop, is that so many people today start programming with our very modern languages, whether it's Java or C# or something like this, and they don't have an appreciation from the languages we came from, which, you could easily just say, oh, well, why do you need to have this history lesson or whatever to learn our modern languages? And the reality is you don't. It's every now and then you bump into a problem that behaves in a different way than you think it should, and it's because you're missing some little nugget of knowledge from 20 years ago, something like that. All right. So what I have found in my profession is more often than not, programmers are people who can are folks who can leverage a language or two rather than folks who have computer programming as a skill set under their belt. And if you can get computer programming as a skill set, you can then apply that skill set to every new technology that comes out without too much trouble. If you don't have that skill set, you don't have that breadth of knowledge about where we came from, you kind of have to put everything in context of what you know, and what you know is a relatively small little bucket. How does Java work, or how does C# work, or something like this. Okay, so we talked about that. So then we started talking about the primitive types. So this is really kind of covering C, C++, Java, C#, even into Swift. So these primitive types really came from C, and what was kind of interesting about it, remember the whole picture here is this is the evolution of languages, and sometimes there's decisions that we made 20 or 30 years ago that seem like ridiculous decisions today. All right, so when we're looking at C, we have bytes, shorts, ints, longs. These are all guys for holding on to whole signed integers. A byte can hold the number 5, a short can hold the number 5, an int can hold the number 5, a long can hold the number 5. Why do we need so many different ways of holding the number 5? So that's when we talked about that idea of the Y2K bug a little bit, and the idea is that we take it for granted today, and for those of us who have been around for a little bit and been in technology for a while, we probably remember when memory was prohibitively expensive. But today, memory is considered to be extremely inexpensive. So I think I used the example of 1996. I bought an 8 megabyte memory chip and it cost $1,000. Today, an 8 gigabyte memory chip would cost $40. Fractions of a penny per megabyte, where before it was hundreds of dollars per megabyte. Inflation certainly doesn't account for all of that. So in any case, memory used to be very expensive, so it used to be on the programmer, from a computer programmer's perspective, to make wise decisions about how much memory they're going to use to represent their values in their program. Now, it's good for us today to be able to appreciate that, because that is part of computer programming as a skill set, to be aware of the impact our solutions have on the computer system and the other resources, because our operating systems today are essentially resource management tools. I mean, from a user's perspective, we think of them as a pretty user interface that allows us to double click on crap. But the reality is we have all these different resources in our computer that a whole bunch of different running programs, most of which we didn't even launch, are in charge of, or kind of vying for, and they need to kind of manage all those things. So in any case, it used to be a major job of the programmer to make sure they made good decisions about memory usage. Today, because of the nature of memory, we can be pretty lazy. Not that we should be, but we could be. And the compiler and the language itself and the linker would all kind of cover up our mistakes pretty well, because who cares if our program uses 1.7 megabytes versus 1.1 megabytes? It's such an insignificant amount of memory in our computer today. It's not that big a deal, but to be a professional programmer, we want to understand the impact of some of our decisions. All right, and this goes even farther than this. If we kind of jump ahead a little bit, let me do this. Kind of put it right here. So while memory, so let's just say things the programmer must consider. So it used to be memory. So we can say not so much anymore. except in extreme cases or something. Memory is not unlimited, but it's very available. But there are other things that we need to be aware of, and some of them are very interesting problems. First of all, we have order NP problems. So order NP problems are problems in computer science that are considered to be difficult to solve. And what's interesting about these problems is in many cases, they don't seem on the surface like they would be very difficult problems. But when you actually get in to solve them, you find that they actually are difficult in various ways. So we'll say order NP are difficult problems, and kind of a subclass of that would be what I would call time complexity problems. And kind of my favorite example of a time complexity problem is the idea of reducing fractions. All right, so if we took the fraction 1/2 and added to it the fraction 1/8, you find a common denominator, you add them together, and then you reduce the numerator and denominator with the greatest common divisor. Well, that seems like no big deal. We learned about that in, whatever, 3rd grade, 4th grade, whatever we learned about fractions. Doesn't seem like that should be very difficult for a computer program to do, or a computer to be able to do if an 8-year-old can do it. The reality is that this is a great example of a time complexity problem. Where I first ran into this was years ago in a programming competition, and I think the assignment, the problem we were solving was something like, you have numerators and denominators that range from 1 to like 999,999 for both numerator and denominator. And you randomly generated those, or actually I think they were given to you in an array. And then what you had to do is you had to add up every fraction that was in the array and ultimately produce your result in reduced form. Okay, no big deal. How do you find the common denominator when you're adding them? You just do the cross multiply thing. You add them together, and then you spin through with a little for loop, and you find the biggest number that evenly divides both the numerator and the denominator. Divide it, you reduced it. No harm, no foul. So you run it on a couple little test cases. Seems to work just fine when you're just reducing one fraction, because you don't really feel it. And this comes down to human perception versus understanding how our computer resources actually function. So the idea here is that when I first ran the program, it seemed to run fine on a little test data set that I gave it. Seemed to run instantaneously. So I felt good about it. I submitted it, and when they actually ran it on the system tests, it failed the system test because one of the tests took more than 30, I think it was more than 30 seconds or more than 10 seconds. Whatever, more than their maximum amount of allowable time to run. So I'm thinking, okay, well, that doesn't really make sense. I mean, is there a bug in the system? So I ran it on my computer, and oh yeah, this did run kind of slow, and then I tried doing an even bigger data set. You could pretty easily give it a data set that would take multiple days for it to finish. All right, so this is kind of why we have algorithms like the Euclidean algorithm. So this is essentially the algorithm for calculating greatest common divisor. All right, nothing's that fancy about it, but the difference between a brute force attack to go and run a for loop or something through all the numbers common to the numerator and denominator, finding the largest one that would evenly divide it, versus using a divide and conquer type of approach like a Euclidean algorithm, is drastically different in terms of performance. And that was a day I kind of learned that lesson about time complexity, is that sometimes a programmer needs to consider how long a problem will take to run. And very often I have found that the problems that are the trickiest are the ones that don't seem complex, but somewhere inside of them a complexity that we didn't previously understand does exist. All right. Now, having said that, let me talk about the other side of the coin, and this is something that a lot of even advanced programmers, I think, fall prey to. So maybe I'll pose the question: do you always write the most efficient code? All right. So this becomes kind of an interesting Interesting question, I guess. And I put efficient in double quotes just for whatever, you decide what that means to you. But so kind of a side story with this one. So one of my companies, I had a developer, gave him a little problem, and this was that he had to work on. And he spent probably half a day coming up with some sort of convoluted mathematical genius-based solution to this problem. That he could have solved with a couple of if statements in 30 seconds. And from his perspective, it was good. Like, oh, this was a better solution. The problem he was solving did not represent an NP problem. It did not represent a time complexity problem. And in fact, his final solution was almost impossible to read. You had to kind of be there in his head to understand the little math trick that he did to solve it. So the question you might say is, was he in the right creating this very, very mathematically efficient solution to this problem versus creating a solution that is easy to read quickly? So this comes down to this question. Do you always, I don't even spell right correct. It's that late at night. Do you always write the most efficient code? I would say it is best to write easy to understand and well-formatted code before writing, we'll throw it in quotes there, efficient code. Okay? To summarize that, make it work and understand why it works first. Then make it work faster if necessary. All right, you will find people that disagree with this statement, but I've been around the block a couple of times with this programming stuff, and I can tell you that 99% of the time, the difference between the most efficient correct solution and the most inefficient correct solution will never be sensed by the user. All right, so at that point in time, maybe the most important thing is for the person who's going to be maintaining that code 6, 10, 12 months from now, who has to go back in and look at your solution. And obviously, programmers are great at commenting their code. I might even throw in here, comment, but don't over-comment. All right, so idea there being is that years ago in computer programming classes, your teacher would have you comment every single stupid line, and that's just ridiculous. You were spending more time. You would write your code, then go back through and comment your code just for your grade. Now the idea here is that in general, code should be self-documenting. What does that mean? That means use meaningful variable names, indent your code, throw a comment in when the code isn't clear as to what you are trying to accomplish. Stuff like that. Okay, so write a comment when it's appropriate, but don't just comment to comment. All right. But as a programmer, we want to focus on being able to go back to our code years from now and pretty much being able to pick up right where we left off. You're going to spend a half hour kind of bringing yourself back up to speed, but you shouldn't be looking at some sort of hieroglyphics at some archaeological dig or something like that. All right, so it's much, much, much more important to write easy to read, easy to understand, and correct code than it is to solve some very, very efficient problem, unless the problem we're trying to solve happens to be one of those time complexity problems or happens to be one of these order NP problems, which typically end up being time complexity problems. All right, but that's going to represent a very tiny fraction of things you may ever run into as a programmer. And you'll know it when you hit it. You'll come up to some problem, just like I used the fraction example there, where it seemed like a very straightforward problem. I didn't even think twice about it, just started solving it because it didn't seem like a hard problem. Sure enough, my solution was correct. It would just take a week to solve some problems, and that wasn't really acceptable. Whereas using the Euclidean algorithm for that thing was That's the thing that would have taken a week doing it the brute force way took, a second to do it the other way. Just more of a math trick, but an important math trick in that particular problem. Okay, so in any case, kind of the high level thing that we're talking about here is this idea that programmers used to have to be worried about a lot more stuff than they have to be worried about today. Okay, the power of our modern programming languages, the power of our hardware lets us get away with a lot that we couldn't get away with before. Now that's good, it gives us that nice feel-good feeling, but we should still appreciate what used to be there, because sometimes we're going to have to lean back on that. There are still problems today that require us to consider memory. So as an example, let's just bounce here real quick. So it's less common, memory, the whole Y2K bug we talked about last time dealt with using two-digit dates for years as opposed to 4-digit years to save memory. Well, that's not a thing anymore. We don't consider stuff like that. But, we certainly, as the types of problems we solve with our computers today get more and more complex, we certainly stumble upon problems that start stretching memory. The good example of this is problems dealing with what are called sparse matrices. Okay, so a sparse matrix, if you haven't seen these before, if you didn't take linear algebra, something like that. So, the general idea of this is we need to spatially represent a large data set where only a few parts are actual data. All right, so a kind of a good example of this is, let's say we have a matrix. Let's just make it sound scary. So we have a 10 billion by 10 billion grid matrix of the United States, where each grid spot is a 0 or a 1. A 1 means that there's a major airport in that geographic spot. A 0 means there's not. So if we take the entire United States, and let's just say there's 10 major airports in the United States. Everybody thinks their airport's major, but whatever. Let's just say there's 10. All right, and I don't even remember now. They say 10 billion by 10 billion. Yeah, so we have 100 billion spots, okay, that we're representing there, and only 10 of them actually have data in it. All right, so now the idea is that we need that to be represented in a matrix sometimes, because we need to spatially know kind of where Chicago O'Hare Airport is relative to where Atlanta Airport is, that kind of stuff. So we need to know geographically where they're related to each other. But the reality is, at the end of the day, we're only storing 10 pieces of information. Most of what we're representing there is relativeness, not data. So we have this gigantic matrix that's going to take up a whole bunch of memory when the amount of data we're storing in there is a very small amount of data. All right, so punchline with this is, this certainly is going to push today's hardware. So even though memory is cheap, we don't have an infinite amount of memory. You'd be hard pressed to find somebody with a computer with like 32 gigabytes of RAM today. I would say commonly, 8 and 16 gigabytes are relatively commonly found. And, we'll fast forward 10 years and you'll find bigger numbers, but the problems that we're solving will probably also become bigger. All right, so our problems get larger, they don't just go away. So it is something we do need to consider as a programmer, but I think that this slide right here is a fairly accurate slide that most people can abide by most of the time. Write code that you can understand, that you feel confident works first. Make it faster if you think you have to. If it feels slow, investigate why it's slow. Nobody cares about a really, really, really efficient broken solution. They'd rather have a working one that's inefficient. All right, so let's go here. All right, so that was kind of leveraging off of the evolution of C++, and then somewhere in here I think we bounced into evolution of Java. So let's talk about that quickly again, and then compare that to C#, because I want to kind of get us to our final punchline today, which is the Swift programming language and those sneaky people over at Apple. So in any case, when we talked about evolution of Java, that was in terms of what was the problem with C++. So the problem with C++ is that it empowered the programmer to make dumb decisions. All right, so just as we just finished talking about, kind of the job of the programmer, how they need to go about writing their solutions, a language like C++ did not make enough of those decisions for the programmer for it to be a true power tool. So that's kind of what we've been talking about today, is we want our tools to do all the work for us, but as a programmer, we want to understand that work it's doing for us. We don't want to have to do the work, though. Okay, kind of human nature. We want to know it all, but have somebody else to do the work for us. So in C++, the example I probably used last time was if you were inviting me to a party, in C++, you could hand me your house and tell me to open the door at 8, rather than give me the address of where your house is. Where in real life, it would never make sense to hand somebody a house. All right. So bottom line is, C++, if you were an advanced programmer and you had already stumbled upon all these little mistakes and learned from them, C++ was a very powerful language, still is a very powerful language, because it gave you tons of flexibility to do maybe non-traditional things. You could pull off something you might not otherwise be able to easily pull off in a different language. Now, when we get to a language like Java, Java took the reins back. All right, so when we compare that to C++, we kept variables, we kept arrays, they dumped structs. Okay, and this was referenced as something we talked about a few minutes ago, and that's from the Java people perspective. They said that, a class is a struct is just a class without methods. So if you want to have a struct, just implement a Java class and just don't put methods in there. There you go, you got a struct. The reality is you only sort of have a struct, because then we have that pass by value versus pass by address thing, which most of the time won't make a difference, but every now and then, if you expect something to work one way and it works another way, you might spend a week trying to debug a problem that ends up being something, it's always something stupid in the end. But usually when you say it's something stupid, it's usually related to some misunderstanding that you had. Okay, so the more things that we can understand about how the simple pieces work, maybe the less error prone we'll be in our coding in the future. All right, so Java removed structs, kept classes in, and then what it did is it, and this is kind of where we started here, so I think this is kind of our last slide we were building right at the end there. So, because we took the C++ side as our starting point. So what it did is it removed a bunch of the required syntax from C++. All right. It's weird that it would actually wrap the plus sign like that. No, well, whatever. So, for example, in a language like C++, you had a special syntax. So we're gonna say no more, no meow, no. Whoa, it's been a long Sunday. No more special syntax for pointers. You can say that means working with memory. All right, so like we said in C++, the programmer was empowered to make those decisions. Am I going to pass something by address or pass something by value? In Java, the programmer doesn't have that decision-making power. They pass something, and Java decides what's the best way to pass it. All right, and then through experience, you kind of get to figure out that how things are usually passed. The reality is, and this is kind of where I nitpick. I almost always use Java as my teaching language in my college courses. Not because there's anything special about Java. I like plenty of languages probably better than Java. But what's nice about Java from a teaching language perspective is I don't have to worry about whether my students have Macs or PCs or Linux machines. They can do their homework in any of their different types of machines because the development tools are available across all of them, because Java is a platform-independent language, which we'll talk about here in a second. All right, but in any case, With Java, they took away the special syntax for pointers. So no longer do people get to make these special decisions. And what I kind of hated about this is a lot of Java textbooks will say that pointers don't exist in Java. We have this special type of animal, and it's very important in programming, called a pointer. All right, and computer programmers are historically terrified of pointers. All right, so what a pointer is, it's a primitive type variable for holding a memory address. Okay, no big deal. The problem is that memory addresses look scary. So it's a variable built for holding something like 0xab12ef45, something like that. Let's see. Yeah, we'll just do something like that. So to us as a programmer, that value looks scary. Okay, this is a hexadecimal value. So now we say, okay, well, why? Why did they represent memory addresses in the scariest possible format? You know, in this hexadecimal value. It actually has to do with what we've been talking about today, about how memory has, gotten very large and inexpensive. Is when we think about our memory in our computer, memory in a computer is like a really long street in a city. And I mean really long, billions of houses long, okay? When we think about a memory, and when we think about an address in real life, okay, you're giving somebody the address of your house. So, it's 123 Main Street in city XYZ in state, AB, whatever it is. So, you're giving them, a multifaceted address that allows them to a human being to dig into the exact place on Earth where that house is. In a computer, it's less complex. In a computer, we have one gigantic street that represents all the houses, all the memory spots, all the addresses that exist in that computer. All right, and we just index them from 0 to 1 to 2 to 3 to 4 to 5, so on and so forth. Okay, the problem is that street is really, really, really long, especially as our memory starts getting up into 16 gigabytes, 32 gigabytes, so on and so forth. Gets even worse on our hard drive side, where we're indexing in a very similar way, and now we're at 3 terabyte hard drives and things like that. So punchline here is that to represent those pointers, to represent those memory addresses, we would like to use a number that fits in the smallest space. We use acronyms in real life. So if in real life, if a word is too long or a phrase is too long, we shorthand it, right? Well, the same thing's true in computers. Well, that's not the only reason. Also, to move between binary, octal, and hexadecimal, there's tricks, so that can actually happen very quickly. But punchline is that a hexadecimal representation of a very, very large decimal number will take up less physical space than the decimal representation of that same number. All right. So my favorite hexadecimal number is BAD. Okay, that's BAD in hex is 2989 in decimal. So not a huge size difference, but we can see one of them's 3 digits, the other one's 4 digits. All right, so punchline is pointers look scary just because they're trying to hold the value in a powerful and short-handed way. But the bottom line is that because this looks scary, programmers are intimidated. So whenever they are working with memory directly, they get scared senseless. All right, pointers become a very difficult thing for students to grasp, even though it's actually no more difficult than any other kind of variable. So working with pointers is the same thing as working with integers or working with characters or working with strings. It's the same stuff. Just the values in there look a little scary, so people get freaked out. Now, if you were a C and a C++ programmer, from back then, you were very accustomed to working with pointers because you dealt with them all the time. You had full control over these things. It would have been difficult to be a programmer back then and not be bombarded with this idea of working with memory. It was a part of your daily life back then. Our modern languages make some of those decisions for us, and a lot of those details have evolved out of our languages. So a modern programmer today who maybe learned how to write code in Java or Swift or C# or something like that likely hasn't been overly exposed to memory. They've probably seen memory addresses before, whether it was in a college course or some error message printed out a bunch of gobbledygook on the screen. You didn't know what the heck it was complaining about. But realistically, with our languages today and our technologies today, working directly with memory addresses is not something we commonly do. Directly. We are commonly working with memory addresses. We're just indirectly working with them because we never have to see the scary underbelly of that hexadecimal number. Right? And part of that's because of this move from a language like Java where it said, we're going to take away, so no more special syntax for working with pointers, working with memory. Java took away that idea. So if we looked back at an older language, like C, let's say, just to kind of give you an idea on how C allowed you to work with pointers. So in C, I can do something like int a is equal to 5. Then I can say int pointer b is equal to the address of a. Something like that. So if I were to print out a, I would get the number 5. If I were to print out b, I would get whatever the address is of a. Okay, so this is the special syntax for getting the address of a value. So here we go. We'll just kind of do it like this. So A is 5, B, address of A, star B is 5. Okay, star B says give me the value at an address. All right, so not difficult stuff once you learn the little simple, kind of cadence here, but punchline still is that this can be intimidating for somebody who's not used to working with this stuff. It's like, oh, well, if why would I need the address of B? Can't I just use it? In a language like Java, if you were to pass an integer into a function, your only choice is to pass that integer by value. You don't get the option to pass it by address. Therefore, side effect is not possible with integers, I guess without a hack. Okay, it's not possible with integers in a language like Java. In a language like C and C++, by default, you would just pass a value a. So let's say we had a function void change, and this guy took in an int a. And whatever a is, we're just going to change it to 7. All right, something like that. So now if we were calling that change value up here, and I called change on A would go in as a 5, it would get changed to a 7, so it would be a 7 only while we're in here, but when we come back out of here, it's back to a 5. It did not have side effect, all right, because it was passed in by value. Now, in C, we could choose to say, you know what? I'm going to go ahead and we're going to allow them to pass this integer in by address. All right, so go ahead and give me the value, give me the address of that variable a. Now I can say star a is equal to 7. And that will change the value of a permanently because I was given the address where I'm going to write to rather than a copy of it. In C, you had this choice. You could choose to do this. And is this useful very often? Probably not. Let's see, once in a blue moon, this might have been helpful. All right, but the people who are proponents of this and who maybe worked on some projects where this was a common occurrence for them, they would complain if they had a language that took this power away from them. In a language like Java, they say, okay, well, rather than you having to worry about these 4 million little special cases, you know what? This syntax, this little star deal here, no longer allowed. You don't get that. You don't get the star, you don't get the ampersand. At least the ampersand, not for that. That's for creating ands in our modern languages. All right, so we're not going to give you a way to directly work with memory in these modern languages. Instead, we'll just make the decision for you and trust us, we're going to make good decisions. And that's mostly true. What I don't like about Java textbooks typically is that they say that Java does not have pointers, which is actually incorrect. And I've mentioned here, there's no more special syntax for pointers. The reality is that more often than not in Java, a variable is treated like a pointer. So things are almost always passed as pointers in Java, as opposed to things are almost always passed by address rather than passed by value. The only things that are passed by value are primitive types. Everything else is passed by address in Java by default. Okay, so that's our evolution of Java. So now to talk about Java a little bit further, let me bounce down here, go right here. So Java's claim to fame, if you will, was this idea that it was platform independent. All right, so that is write once, run anywhere. All right, so this kind of becomes an interesting story. So consider when Java came out, kind of the late 90s or so, made by Sun Microsystems. There was like many things, there was a perception that there was a problem in the world of computing. And the perceived problem was that software was available on Windows first and perhaps never on Mac. That was the perceived problem. Okay? Now the reality is this. I guess we don't really. They were supposed to implement some sort of show of hands thing here. You can just post in chat if you're interested in answering. But how many of you are PC people versus Mac people? So just kind of type in there PC or Mac, whatever your favorite thing is. And while you're doing that, just from an interesting thing. So okay, 1-to-1 right now. So now what's kind of interesting about this is. Like I said, this was a perceived problem. And the reason it's a perceived problem, and even our Mac person there, Edmund, would probably admit to this, who is louder? 100 Windows people or 5 pissed off Mac people? So Apple, I guess I call it. Well, first of all, I'll say I'm a Mac person. Not necessarily because I think the Mac is the better machine. They're the same crap. Mac is like a Cadillac. A PC's like a Chevy. They're both going to get you to work. The reason I think a Mac is the right tool for the job for most technologists is it's 2 machines for the price of 1.7. So I do development most of the time I'm on the Mac side, but if I have to do .NET stuff and I'm going to be working on a project for a prolonged period of time on the Windows side, I'll just dual boot into Windows and be working on Windows. Otherwise, if I just have to do some testing stuff on some Windows things, I'll just virtual machine it. But punchline is that a Mac lets me work on both platforms for the price of 1.7 platforms. So when you look at it from that perspective, a Macintosh is actually a reasonable value. If Grandpa wants to just check his email, getting him an iMac is probably not a best use of the funds. You should get him a budget pleaser HP or possibly an iPad. Now we're back giving money to Apple again. But, punchline is that in general, Apple people complain louder. Okay, so when I say there was a perceived problem, that was because the people that were getting screwed, quote, were the Mac people who were not getting the software that all the Windows people were getting. And remember, the way that software was distributed back then was very different than it is today. The whole model's different now. Back then, if you were a software writer, you had to find a publisher, just like books. Okay, you had to find a publisher. You had to go through the hoops of getting it on the shelf at a Best Buy, and people were taking their cut and all this stuff. You needed to have as large of a market as possible, and I don't care, what kind of drugs you were on as a Macintosh user. There wasn't any lens you could look through that made Apple look more popular than Windows. You still can't today, okay? Microsoft's never losing their dominance in the desktop operating system. Now we're over into mobile, so now you have Google and Apple kind of running the show over there. So we're getting into, mobile's kind of replacing the desktop more and more every single year. So Microsoft is obviously going to be moving out of you know, in importance from that perspective, but they're never giving up their. I think you know, Apple brags that they've made larger headways in the last 5 years into the desktop market than ever before. I think maybe Microsoft's down to 95% of the of the market or something like that. It's not even close is the punchline. But you know, the idea was there was a perceived problem, and Java had offered a solution to this problem. That solution was, okay, people, if you're going to start, if you're writing software, so if, you know, up to that point, if you were writing software, you'd probably rewriting it for Windows because that's where the biggest market was, and that was your chance of making money from your software. Especially given the hoops you had to jump through to get it on the shelf somewhere. So now the Java people say, hey, now you can still write that software one time like you did before, but now that software will run on any machine. It'll run on Windows, on a Mac, on a Linux machine, on a Unix machine, so on and so forth. Okay, and the way that pulled this off is through something called a virtual machine. Specifically, the Java virtual machine. And let me just show you kind of a graphic here. If you remember, I think we talked about it up here. Let me just see if we kind of had those slides. Yeah, so remember up here there are 3 kinds of programming languages. We have machine language, low-level language, high-level, and we talked about the CPU specifically. All right, same thing, we had compiled and interpreted languages. Java kind of represents a little bit of a blurry area here. So we come back down here to this Java slide. Make this guy left justified. So you would start with the Java source code, which would then turn into Java bytecode. Okay, so this is a high-level language. This is a low-level language. And to go from a high-level language to a low-level language requires a compiler. So this is a compiled move. This goes through the Java compiler, which converts high-level Java source code into low-level Java bytecode. That low-level Java bytecode is then run through the Java virtual machine. The Java virtual machine is an interpreter. Interpreter. All right, that guy is an interpreter. And the Java virtual machine then converts bytecode into native assembly, which is directly understood by the CPU. Okay, so this is the path for how a Java program works. So you write your Java program, you compile it into bytecode. This Java bytecode looks the same whether you're on a Mac, on a PC, on a Linux machine, it doesn't matter because that Java bytecode is written to be understood by this computer program called the Java virtual machine. All right, so what Sun Microsystems, the makers of Java, did is they wrote the Java virtual machine multiple times. They wrote it for Mac, they ported it for Mac, they ported it for Windows, they ported it for Linux, they ported it for Unix. So rather than requiring the developers over here to write their software zillions of times, Sun Microsystems did that work. They said, we'll just write our product multiple times so that everybody understands it, so that all the sides can understand it. Okay, now the problem with this, if you remember us talking about those languages before, we said that compiled languages tend to be fast. Interpreted languages tend to be slow. Okay, well now this is kind of problematic because now we have a fast piece and a slow piece here. And the issue here is that in the early days, Java was kind of promoting itself as a language for making video games. All right, and that never really, because that's really where people were complaining early on. Not the business world, but it was like, oh, well, the video game XYZ came out for Windows, but not for the Mac. All right, so Java was kind of weak in that spot because even though Java is faster than most of our modern interpreted languages like Python and PHP and stuff like that, it is slower than our native languages like C++ and C# and those guys. All right, so to put this in context, let me steal this slide. And I'm going to throw, well, just put it right after this one. Evolution of C# in here. We're not going to spend very much time on this one because it's pretty much the same thing as Java. But we can say this guy, he brought back the special syntax for pointers only inside an unsafe code block. So basically they said, okay, you want to be dangerous again, that's fine. We're just going to make you throw it inside of a code block that says unsafe. Fine. So yeah, you get your cake and eat it too. But more importantly to us from the C# thing is, originally Microsoft tried to steal Java. Then they got sued by Sun Microsystems and lost, and things like that. And people try to demonize Microsoft for this, but the reality is it's our legal system that allows this type of stuff. If you're a company like Microsoft that has all this money, most of the time the path of least resistance is to steal something that you want and then get sued and pay the penalty, rather than negotiate for months on hand to buy it outright. It doesn't sound ethical, but it's just the way the world works today. So I guess, I'm not necessarily a Microsoft fan, but I also don't want to demonize them for something that all the big companies do. Microsoft just happened to be a very, very big fish in a very, very big pond, or I guess a relatively small pond back then, where it was really noticed. But in any case, they lost the lawsuit, blah, 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 were forced into coming up with their own language. That's where C# came in. And C# actually, right after I got done making fun of Microsoft for they should be able to steal stuff, let's look at the C# model. So we're going to start with C# source, which runs through a compiler, which turns into, you can't call it Java bytecode, so we're going to call this missile code. That's Microsoft Intermediate Language. Same thing as Java bytecode. We can't call it the Java virtual machine, so instead this guy's going to run through .NET and then get interpreted into native assembly language, which runs on the CPU. All right. So even though we've changed a couple of words here, these models look pretty identical. But there's a small little change here. There's one more little piece. And that's something called a JIT, a just-in-time compiler. So if any of you have ever done .NET development, what ends up happening is the very first time you run a .NET program, it runs a little slower. It actually doesn't run slower. It takes longer to start. And the reason it takes longer to start is it's going through this just-in-time compiler just that very first time. And it's doing this interpretation from missile code into native assembly for that machine, but it's only doing it one time, not every time you run that program. So from that point forward, that program runs as if it was a natively written program on that CPU. All right, so you get all the performance of our prior languages with according to Microsoft, the platform independence of our modern approach. Now, for those of you who've been in the development world, you might not necessarily think that .NET is platform independent. According to the Microsoft people, you're very wrong. See, .NET is completely, all the .NET languages are platform independent. Okay, you can write C# code on Windows, on a Mac, on a Linux. You can write it, and it will run on any platform in the world that supports the .NET component architecture. The problem with that is that unlike Sun Microsystems that ported the Java virtual machine over to all these different platforms, Microsoft was a little bit more protective of their .NET architecture. So when they say that that it will run on anything that supports the .NET component architecture, they're basically saying it'll run on any platform as long as it's Windows. All right, but now Microsoft has more recently said that they're open sourcing. I don't even know if it's open sourcing, but they're open architecturing .NET. So you're going to be able to see some of the projects be more cross-platform. We've already seen there's a project on the Mac side and the Linux side called Mono. And the Mono project allows people on the Mac and Linux to write C# code. And Mono tries to emulate the .NET component architecture. All right, but punchline is, let's just say that Java and C# are pretty equivalent technologies, with the difference being that C# probably has the higher performance because of .NET. Okay, but understand that C# has really no performance on anything but Windows because .NET's not on those other things. And nobody would use Mono for a real I guess, a real project. That's probably not fair for Mono fans, but in reality, that's probably a true statement. Okay, so now, the moment we've all been waiting on. Remember all the way back here, one of our early slides, this guy up here, we kind of drew out this picture. And we spent our first session talking about kind of our web languages and how these guys evolved. We spent our next couple of sessions talking about how these languages kind of evolved and all the little pieces in between. Okay, and what we didn't talk about here is kind of Objective-C. We can just talk about it here at the high level real quick, is that right in here when we made that jump from C to C++, or we can just say generically, we made the jump from procedural languages to object-oriented languages, we started seeing, we adopted the object-oriented languages, but this was right in the middle of the Apple Microsoft war. So Apple jumped on the Objective-C bandwagon, which is object-oriented C, just a different take on it. Microsoft jumped on the C++ bandwagon, and that's where they had their lineages. So this was Apple over here, and this was everybody else. Okay? But from an Objective-C perspective, you might as well just pretend these languages are C++. All right, we would have those same arguments in there for those guys. All right, but now we're interested in Swift. So let's kind of finish that up, and we will call it a day. So we have evolution of Swift. All right, so what did Swift do? They kept the variables, they kept the arrays, they brought back the struct. Remember, we said structs should have never gone away because they weren't actually classes without methods weren't actually equivalent. All right, they kept the classes. We can say they have the special syntax for memory, but it's not promoted. So kind of the idea is that if you want to have access to it, it's there, but it's not something that's part of like this Swift way of doing things. And that'll make sense when I kind of tell you the punchline here in a minute, because Swift has some overarching goals. All right, so we're going to throw a couple of them that they were obvious about, that they said they have these. So one of them is reduce the amount of extra characters a programmer had to type. All right, so that's one of the extra goals of Swift, to the point of like removing parentheses from if statements and removing semicolons and things like this, things that our programmers over the years had become accustomed to. But wait a minute, notice I just said semicolons. So if we go back up here, when I say semicolons, who's accustomed to semicolons? Well, these guys all use semicolons. These guys all use semicolons, okay? But a lot of these guys over here don't. Python doesn't use semicolons. So, the idea is that Swift, it's very easy for us to assume Swift evolved out of these languages. Okay, but I'll show you the punchline here first, and then we'll talk about, just for a few minutes, we'll just go a few more minutes just to kind of finish off the whole topic. But a lot of people, when Apple advertised this, they were kind of talking to their Objective-C code base. So they're saying, hey, iPhone and Apple developers out there, I know it's been a long time and you've been working with this archaic language, and Objective-C 2.0 wasn't really anything new. We just had to pretend like we upgraded it. Finally, we have a brand new language for you, and it's completely evolved, and it's better than everything else out there, and it has time travel, and that's made up, but, whatever. The problem is, just like we said earlier, that the only people that were complaining in the Java days were the Apple people. None of the Apple developers, none of the people who were using Objective-C as their main language had a problem with Objective-C. In fact, even to this day, I might say Objective-C is one of my favorite languages today. So outwardly, the rest of the tech community listens to Apple say that, we've finally done right by our Objective-C developers. Now, these guys have been drinking the Apple Kool-Aid for years. They love Objective-C. No problem. Swift was not for these people. And when you look at the Swift language, it doesn't look like Objective-C. It has the libraries in there from Objective-C. That way you can still write your iOS and your Apple stuff, but the syntax of Objective-C looks a lot like Java. It looks a lot like these web languages over here. Okay, so what was Swift? Swift was Apple saying, hey, Android developers, why don't you come over to the dark side and write some iOS stuff? Hey, HTML5 developers, rather than writing your cross-platform mobile applications, why don't you come over and write some native stuff for iOS and Apple, iOS and the Mac? Okay, Swift was not targeting the existing Apple developers. It happened to have that effect in the end, but it really was a matter of creating a language that was friendly, visually friendly for the Java and the web developers to make the trek over here to the Apple side of things, because Objective-C, out of all these languages, was probably the language that was the most visually intimidating. Okay, if you look at Objective-C, it looks very different than these other languages just because of this transition right here, where they basically had to say, okay, well, C++ looks like this. We're not going to do what Microsoft does, so we're going to make our stuff look completely different. All right, so they almost just forcibly made Objective-C look different. All right, so that's why it was kind of intimidating. But what we see down here then in in Swift is they had this main goal of reducing the amount of extra characters, but they also have this other thing is add as many comfortable structures into the language that will make developers from other languages feel at home. Okay, so this, in my opinion, is one of the problems with Swift. In Swift, there's like 30 ways of writing a loop, because you have all the loops that some of the web developers might be familiar with, and then you have, for something in a set, for something in a range, and then you have your normal traditional for loops and while loops and things like that. You have a whole bunch of different ways of accomplishing the same stuff, so that people who are coming in from Python or from Ruby don't have to change their mindset. They can immediately jump in, learn the Swift syntax, and go to town. Having said that, I don't dislike Swift. In fact, I probably primarily do most of my development today in Swift. But I would say I'm not necessarily enamored with the language. I think there's other languages that I prefer over Swift. I think the reason I do so much stuff in Swift is I like the Xcode development environment for writing iOS stuff. So I like that tool set, not so much the language. I'd rather the language probably be a different language, but whatever is kind of the punchline there. Okay, so I think that pretty much kind of covers the last 40 years, let's say, of programming languages, and gets us up to our modern guy Swift. And we know that every other week there's a new JavaScript-based technology over here, React and Angular and all those things. So, but the punchline is hopefully after going through this workshop, you now have this appreciation for all of these technologies that have existed over all these years, and we realize that they're all much more similar to each other than we might otherwise think. There's just a couple of little evolutionary parts there where we made a jump from one language to another and had to change our mindset just a little bit. Okay? So, in any case, I'll hang out for a few minutes if you have any questions. This workshop will probably happen again. I think we're going to keep the same time, but I think we're starting over. I might, if any of you have requests for other topics you'd like me to cover, feel free to shoot me an email, and I'm happy to run a separate workshop for some of that stuff. Here's my thankful email address. But I think this time slot here, we're going to start the Evolution of Programming Language workshop over again. So that'll probably start next week, I would assume. Possible we'll skip until after Christmas. But in any case, I'll hang out for a few minutes if you have any questions, and I'm happy to answer them. Otherwise, I will see you when I see you. Let's see. Learning Python, what's a good second language? Are you doing just straight Python, or are you doing web development with Python? So, I mean, I guess, this kind of gets down to this concept that they refer to as something called full stack. That would have gotten interesting pretty quickly. Something called full stack. So the idea is that what's full stack? This is kind of being familiar with, let's just put in quotes, all the tech for delivering applications on multiple platforms. All right, something like that. So if you're learning Python right now as your first programming language, nothing wrong with that. In fact, Python is actually a fairly friendly first programming language. In general, the web languages are good first programming languages because they are a bit smaller, so a little bit less intimidating. So are you just writing stuff that you're running out at the console? So are you doing the Thinkful course in Python, or are you doing kind of Python on your own? Okay, so you're doing the Thinkful course on Python, and so as you go through that, and you're in the normal one, not the data science one? So you're doing the pirate bartender and the bicycle industry, all that stuff? Okay, got it. So, that course is going to start off kind of teaching you programming as Python. So you do your pirate bartender, and you're learning about dictionaries and lists and stuff like that. And so in any case, from there, they're going to transition you into writing web applications. So right now, as you're writing your Python program, you're using Python syntax with a console front end. Okay, that's what you're writing right now. Okay. So all your interfaces are text-based interfaces. What's going to end up happening in that class is you're going to go with Python syntax and move towards a web front end, and you're going to accomplish this through a couple of tools. One of them is going to be a tool called Flask, which is a built-in web server for Python. And then you're going to also use, I think they use Jinja in there right now. So you're going to use Jinja as a template engine. And that's for accomplishing, if you remember last time, I think we talked about we talked about MVC, some of the design pattern stuff. We have them somewhere in here. Yeah, MVC. So it's a good idea to separate your code from your designs. So punchline is that if you were writing, let's see, where's my guy here? So when you write your web front end, you're going to be writing HTML and JavaScript and CSS stuff, and you're going to have to be talking to a Flask web server, and Jinja is going to be the tool that allows you to write your HTML in one place and write your Python in another place, but somehow get your Python logic into your HTML documents. All right, so this little list right here, this is effectively writing a web application using MVC. Okay, that's what you're doing there. You're writing a web application using MVC. You happen to have chosen Python as your back-end programming language, and you're using HTML and JavaScript and CSS as your front-end programming language, which every human being who writes web applications will use. That's what they use. All right, so after you get done with that course, you will have so I mentor that Python course as well, and then I mentor the iOS and the Android course and those guys. So what I would usually recommend to my students is after you come through that course, you kind of have the idea of writing software for a web front end under your belt. So when you ask what language should come next, I would twist that and say what technology would come next. So from my perspective, I would say what makes the most sense, what I typically have my students do, and I would say I have a pretty high rate of students staying on for a second course with me, is what we end up doing. I ask them, are you a Mac or a PC person? If they're a PC person, I encourage them to do the Android course. If they're a Mac person, I encourage them to do the iOS course. Because what are you doing in those courses? If you're doing one of the mobile courses, now what you're doing is you're using, either Swift or Swift or Java syntax. for a mobile front end. So now you're instead of using HTML and JavaScript for designing your interfaces, you know, your text boxes and buttons and stuff like that, now you're using the infrastructure, more of a native infrastructure for having buttons and things like that on either an Android device or an iOS device. I would clearly say that iOS is the better platform. But if you are a PC user, I don't necessarily think it's worthwhile going out and buying a Mac to do the iOS course when having competency in Android pretty much translates directly over to iOS. You can, you know, once you know one of them, learning the other one's pretty easy. So let's see, if I scroll up here, did you say you're a PC person, right? Yep. So given that, I would say that your next technology should be Android. Whether you do that with Thinkful or whatever, and you know, I'm happy to work with you if you'd like to do it with Thinkful. Just request me and we can connect up. But that would be what I would suggest, and that's going to take you down this path towards full stack, where you're going to have a global understanding of all kind of little different nooks and crannies that you need to know to kind of deliver applications. Make sense? Yeah, perfect. Good to hear there is a next step. I guess that means you don't hate it. All right, any other questions? Going once? Going twice? And I guess feel free and come back next week at the same time if you want to see the same material again, but I think we're going to be starting over. But like I said, if you are interested in another topic for me to cover in a workshop, I'm always looking for a topic, so feel free to shoot me an email and request something, and I can try to put something together. All right. Well, I will put the final video up, and somewhere we'll put a link to all the different sessions we did. I recorded every one of them, so you can go back and review and all that jazz. But in any case, I will see you when I see you. Take care. Bye-bye.